Well, welcome back to part 3 of why tube amps sound different. What you see is a rather busy chart that I will not try to explain yet, but we will get back to this a little bit later. But first, what I would like to do is review a little bit of where we are and how we got here. And for that, you may recall that we started out looking at nonlinear elements in tube amps and the role that they play in the distortion that makes tube amps sound differently. Now, we looked initially at speakers, then we looked at transformers. We have not really looked at tubes that much, although we did do a series using the 570 on various triodes and pentodes and beam power tubes. And finally, we didn't do at all anything about power supplies, but power supplies also affect the nonlinearities in amplifiers. But the main differences between a solid-state amp and a tube amp is in the transformer and to some extent the tubes. Now, you can make solid-state devices, MOSFETs, that work very much like tubes. But let's be honest, they're not nearly as, pardon the pun, as warm as tubes are. But mainly it's the transformers. Now, we talked a bit about speaker impedance changes. We then talked a little bit about transformers and the effect of hysteresis. We didn't talk much about leakage inductance. I've previously done a video on that. And at the end of part 2, I touched briefly on auto-transformer action. We have already talked about primary-secondary interaction, that is how the output load reflects back from the secondary into the primary and affects the load on the tube. And I promised that we'd do as little math as possible and graphical analysis as much as we can, picture worth 1,000 words. So we've done these experiments. Now what I would like to do is talk a little bit more about theory, but let me explain that I'm not trying to make to achieve any particular result here. In general, I suspect that there are, well, several types of viewers. Some people aren't interested much in this. They probably have tuned out already. Some are only interested in watching enough to learn something that they can use the next time that they get together with their technical group or whoever, and you may already be there. But then the last two groups are those that are very curious about things. Some people might say obsessive, but we all know that we're not obsessive. We're just curious. And finally, those that really would like to look at this from a professional standpoint, maybe because they want to design their own tube amp, or maybe they just want to study it in more depth and become better at it so they understand all of the nuances. Now, if you remember, we started the series with a video by Uncle Doug in which he suggested that that you not try to do your own calculations for load impedance on a tube. And as I said then, I agree with that advice. But if you do want to know more about how to calculate, or at least how others go about calculating or determining experimentally what the right load impedance is for their particular design, well, stay tuned. By way of further review, we looked at how the power output, the total harmonic distortion, the third harmonic and second harmonic distortion varies. And in this case, this is for a 6F6 pentode. The reason that these sorts of things are important is one of the choices that you need to make is where are you going to operate the tube? Well, at what load impedance are you going to operate the tube? And we discovered that because of hysteresis and other nonlinearities in the transformers, that you don't get a straight load line. That instead what you get is a parabola. In other words, the tube operates around this path, not straight up and down like a resistor. What I would like to talk about now, well, there's two topics. First topic is, how do you decide what the best operating point is for a particular tube or a particular amplifier using a particular tube? And for that, I'm going to go back to a paper that appeared in the Proceedings of the IRE back in December of 1941 called Optimum Conditions for Maximum Power in Class A Amplifiers. And rather than read you that paper, what I have done is more or less abstracted the important parts. Slide that out of the way. And what that author talks about is that early on it was realized that when you're operating with very small signals, that the optimum plate load is the plate resistance of the tube. However, if you want to get low distortion, you tend to operate at a load resistance approximately twice the plate resistance of the tube. Now, if plate resistance and this doesn't make a lot of sense to you, go back and watch my video on tubes. I think it's 081 or 082. One is on how tubes work and the other is on vacuum tube circuits. The second or third factor that you need to consider is plate dissipation. And if the plate dissipation is an important factor, you might need to operate at up to 15 to 20 times the plate resistance of the tube just to keep the tube itself from overheating at its quiescent or its static operating point. So how do we do that? Well, with an inductive plate load that is a transformer, realizing that impedance varies with frequency, that we have hysteresis effects, we have reflected impedance from the speaker, and losses. And finally, in a little bit, we'll get to push-pull amplifiers and the fact that we have auto-transformer action. Now, we've talked about most of these either in one of the previous videos on why tube amps sound different, or in a previous video of things like output transformers for tube circuits. But what first choice that you need to make is, do you want to use a triode, a pentode, or a beam power tube? And do you want to operate it single-ended or push-pull? Also, do you want to use an ultralinear style of design? And if so, you might want to look at my videos 169 and 172 that talk about the difference between the ultralinear and the Williamson, which was one of the first true high-fidelity amplifiers. Actually, I think it goes back to 1947. It's in Wireless World. Anyway, if you look at these videos in that series, I talk about that. And then finally, like I say, if you want to review transformers, look at 185 and 186. Those might give you some ideas. But for right now, I'm just going to do a quick review of what we learned. I'm finishing up with, remember that a transformer is just a way of magnetically linking two circuits. We use Ohm's law for AC, which is impedance is the voltage divided by the current. We look at the voltage ratio, that is from the primary to secondary or from one winding to another, and that is equal to the turns ratio. Here I call it TR. The impedance ratio from one winding to the other is the square of the turns ratio. So if you remember, here was an example. Here we have 4 turns on this and 2 turns on this. That means that if you apply 4 volts here, you will get 2 volts here. The current, however, is inverse. If you have 2 amps flowing in this AC, you will have 4 amps, or if you properly load it, you will have 4 amps flowing in this side. In other words, the voltage follows the turns ratio. The current is the inverse of the turns ratio. Then we noted that if you have a transformer with a turns ratio, for example, of 2 to 1, that means that with 4 ohms on one side, you will see 1 ohm on the other. Or, as shown here, if you put a 1 ohm load on this side, the 1 of the 2 to 1, you'll see 4 ohms on that side, which is, of course, what the tube sees. That is, the impedance is just the turns ratio squared. Now I'd like to turn to the subject of push-pull amplifiers. A push-pull amplifier normally has a pair of tubes, the plates of which are connected to the opposite ends of a tapped primary output transformer. Now, there is a plate supply, which is normally connected to the center tap of that transformer, and the load, which normally would be your loudspeaker in an audio amplifier, is connected to this winding, which is called the secondary. Finally, there is a bias value on the input that biases the tube for its operating point. Remember that an operating point is just the place where it could be anywhere along this load line, but it's the place you choose that the tube operates at when there is no signal. When there is a signal, of course, with a transformer, as you remember, it doesn't stay at the operating point. Instead, it moves around the ellipse that is formed by a transformer. Before we actually get into the push-pull stage and how you can calculate the effects of the transformer and of the tubes and the operating point on the operation of the output stage, I did want to go over something that I covered at the end of part 2, but I realized later, a couple of people asked some questions, and I realized that I may not have been as clear as I could have been. Well, that's true all the time, but maybe I was especially unclear there. As we saw already, the voltage follows the turns ratio. The amperage is the inverse, and the impedance is the turns ratio squared. So consider the output transformer like the one we just looked at, where there are a number of turns on one side of the primary, exactly the same number of turns on the other side, or at least you hope they're exactly the same. And that means that the ratio of the turns plate to plate is 2n to n. In other words, each tube sees n, but the whole circuit, due to auto-transformer action, sees an impedance of 2n. Sees a turns ratio of 2n. There I go again, mixing up the terms. So the turns ratio is twice as many turns for the total as for either side. To get the impedance ratio between plate to plate and single-ended, you have to square the turns ratio or get 4 to 1. And that's the reason why that the transformer in a push-pull stage is rated plate to plate, not single-ended. So here is an equivalent circuit of a Class A push-pull amplifier. Once again, on this side is the load, the speaker, the secondary of the output transformer, the individual windings of the primary, which are tied together in the center, It's called a tapped primary. We apply a signal to one side and the exact same signal to the other side, but notice that the polarity of this signal is the inverse of this. So in other words, when this signal is going positive, this signal is going negative. That is done because the grid voltage that is applied to the tubes, e.g., is positive at the top here, which means that G1 is positive, when G2 is negative. Notice it's on the opposite side of the plus sign. And then we multiply the amplification factor by the grid voltage to get the voltage at the plate of the tube. And that voltage flows through the plate resistance of the tube. Remember that when you're doing these sorts of analyses, these sources are essentially short circuits in terms of impedance. They just produce a voltage, plate resistance, and then you have whatever resistance and impedance there is in each winding, and then the auto transformer action between the two, which causes you to get the 4-to-1 impedance transformation. Okay, about this time, all of those that were just looking for something to say at the next party are long gone. So those of us that are left, this is a simplified equivalent circuit in which we just look at the load that the tube sees as RL prime. This is the current in that loop, and we no longer are looking at the grid voltage. We're just looking at the voltage of the two tubes, their respective plate resistance, and the equivalent plate-to-plate load impedance. And finally, we get to the point of this video. If you plot the composite plate characteristics of the push-pull stage, we just saw an equivalent circuit and a simplified equivalent circuit. The load resistance is just the slope of this line. And notice right here, each of these represents grid voltage. And of course, this is plate current in one tube, and this is plate current in the other tube. Notice that in this tube, when the plate current is going positive in this tube, or increasing in this tube, it is decreasing in this one. Vice versa, as this one starts to come down, the plate current in the other tube starts to go up. But because they are connected out of phase with each other, 180-degree phase reversal, what happens is the composite, instead of having these curves that a single-ended tube will have, the curves tend to match each other. Notice that this curve and this curve, if you add them up, what you find is that as this one starts to curve over and slow down in terms of its speed, this one speeds up. So it's almost like you have, well, maybe I shouldn't go there, spooky action at a distance. It's as though these two tubes are linked to each other, and in a sense they are. They are linked through the autotransformer action. And the result is that the characteristic of that tube operating in conjunction with this tube causes it to be a relatively straight line. Now, understand, this assumes that your transformer is perfect. This assumes that your tubes are perfectly matched. No such thing really exists. However, it comes pretty darn close. Now, why would you want to do that? Let's take a look at the path of operation. Maybe we need to back off a little bit here. Now, this is for a triode, but the same thing is true of a pentode. The tube itself operates along this path. The other tube operates along this path, but the circuit, the combined push-pull circuit, operates along this straight load line and along these characteristic curves. So what we have done is we have straightened out the actually the even harmonics by balancing the tubes and balancing the transformer. And finally, we're back to the chart we started with. I'm going to turn it this way, and this assumes a plate voltage of 250 volts and a grid bias of minus 55. These are various plate resistances that are drawn here. For example, load resistances. That's 3,000. The next one is 2,500 ohms, 2,000 ohms, 1,600 ohms, 1,300 ohms, and I think 1,020 ohms. So why, or maybe more importantly, what does that give us that we wouldn't ordinarily have? Well, what we are able to do, this is a chart of a type 45 tube. And a type 45 is a pretty old tube, but it because it appears in a number of the older tube books, I'm using it here. This is the effective power output. This is the average plate current. And this is the harmonic content. So, if you choose a particular value of grid bias, you wind up picking a particular value of harmonic content and a quiescent plate current. The quiescent plate current multiplied by the quiescent plate voltage, remember, is the plate dissipation. You cannot exceed the plate dissipation rating of the tube you are using. So, what does that look like in a particular amplifier? Well, this is a plot for a 6L6 push-pull stage. These are the various grid voltages. We are going to assume that our operating point is here, and this is the voltage on the plate of one tube, starting from 0 and going up to the right. This is the voltage on the other tube, starting from 0 and going up to the left. These, of course, are the characteristic curves. If you've watched any of the videos I've done with the Tektronix 570, this is a typical beam power tube plate characteristic. This is flipped down here for the other tube, and then across here is the ideal plate resistance. Now, why do I say ideal? This is the plate resistance that allows you to get the highest power output from a pair of 6L6s. And this assumes that the plate voltage for each tube is 250 volts, and the grid bias is minus 15 volts. Now, let's compare that. And by the way, this is from the book Radio Electronics, which you can download from the, I think, tubebooks.org, I guess it is, that shows the difference. Notice that with a single, that is a single-ended, your load line is actually doing this. Compare that to what a push-pull can do. Why would you care about that? Well, here, from that same book, page 204, shows what happens when you put two tubes in push-pull. Suppose that you have a very nonlinear characteristic out of one tube, in other words, this big curve here, and the same characteristic, identical but in the other direction, in the other tube, so that The positive excursion of this tube is too much, the negative excursion is too little, and in the other tube it's exactly the opposite. Well, the push-pull stage will actually average those together and produce an output which has virtually no even harmonic distortion. In other words, the second, the fourth, the sixth, the eighth harmonics of the input signal are suppressed by the push-pull stage. Now, for those of you that have stuck with it, we are now essentially working from this. Let me zoom in on the title. We are now working from this paper, Graphical Interpretation of Performance of Push-Pull Audio Amplifiers by Thompson. This appeared in the April 1933 edition of the Proceedings of the Institute of Radio Engineers. Once again, radiohistory.com has these magazines. You can download them. If you look in the index, look for IRE in the index. It'll say IRE Proceedings, not Proceedings of IRE. So if you look for those, you can find this article. Go to the April 1933 edition. And I'm not going to go through the analysis here. But for those of you that really do want to learn how to do all of this, you will see that what this article is about is exactly what we've been talking about. And in fact, that chart that we started out with and that we just now went through for the second time is the characteristic that the author uses for the particular article. And his conclusions are summarized in this chart, which we just looked at, showing the comparison between computed and measured values of a power output. Now, in this particular case, he uses a Type 45 tube. Now you see why I started with a Type 45 in the early part of this video. But this article or a paper started a lot of thought in the amplifier or electronic community about how to optimize the performance. What you want is you want the most efficient output stage that you can get at preferably the lowest cost, but that meets certain other criteria like distortion. And this particular paper is really, I think, regarded as the seminal paper on the operation of push-pull output stages. Now, I'm not going to go into the mathematics, but basically what he is saying is that you operate this tube at the operating point that is determined by these composite characteristics. And that is how the plate-to-plate resistance in the tube manual that Uncle Doug recommends you just use, he's right, but a lot of thought and a lot of experiment went into getting that exact value. If you have a very good transformer and you have a pair of very well matched tubes, you can come very close to these theoretical values. So I hope this has been helpful to the people that are interested in studying in more depth how a push-pull stage works, and a reference that will start you down, I can tell you from personal experience, a very long journey, but also a very interesting journey. At least I think so. So, once again, I thank you for watching. I hope you got something out of this. If you stayed with me this long, I hope you got a lot out of this. And look forward to some new things I think at this point I'm going to close off the how or why tube amps sound different, but may come back to it at some point in the future. In the meantime, have a nice day.